Hello everyone, welcome. Now we are going to explain about our project Effective Hoist System for Material Transport in Slope Stabilization Project. In Sri Lanka, hills area need to slope stabilization to prevent landsliding. Our selection location number 147 Ella between Badulla and Bandarawala railway station, Badulla district. The orange line represents the public transport by using vehicles and red one is train track. We can't use vehicle to transport materials to the construction site. We only use train to transport materials till base of the slope. We have to transport those material to construction level. That's why we need a hoist system here. Our site conditions by analyzing plane span 66 meter, height 29 meter, width 60 meter and slope angle 26 degree.
As we mentioned earlier, the site conditions at Damodara make material transport extremely challenging. So to move material safely along the slope, we need a suitable hoisting system. To find the best option, we studied several types of hoisting systems commonly used in slope stabilization work. The first one is rail-based hoisting system. These systems use steel rail fixed along the slope with a trolley that moves on the track to transport material. They are quite stable and can carry heavy loads, but the installation is expensive, needs advanced engineering and work only for shorter spans. So in our case, it's not practical. Next, we look at tower cranes. They are great for lifting heavy loads and are highly standardized, but the site has very limited space, unstable soil and no room for a proper foundations. Plus, installation and operating costs are very high, so this operation was ruled out too. Then we considered the live skyline system, where one end of the main rope is fixed downhill and the other is connected to a winch at the top. Its low cost can cover long spans and allow tension adjustments as well, but the anchors must be extremely strong and the load capacity is limited. Finally, we evaluate the fixed skyline system, similar to the live skyline, but here both ends of the main rope are fixed. It's much more stable, cost-effective, and suitable for long spans. We can even add a mid support to reduce cable sagging and increase stability. We also reviewed other systems like the one rope, two rope, and three rope skyline systems. While the three rope setup provides high stability, it's too expensive and complex for our purpose. One rope system is very simple system where single rope is only used to move the load. Load can be moved only downward direction under the gravity. Because only one rope is used, there is a safety concern and the one rope does not meet our design concept. After comparing all these systems, considering the slope length, cost, safety, and available resources, we selected the fixed skyline system as the most suitable design solution for our project. Next, let's take a look at the key components and how the design was developed.
Let's come to the design of two-rope fixed skyline system. We have three parts. First one is material loading place. Second one is unloading place at the top, and middle support for decrease sacking of rope. Instead of conventional pulley, we have a custom pulley design. It has two pulley connected with a U plate and bucket is connected using hook. You may think, will it flip and fell down? For that we designed pulley and bucket's center of gravity always staying in left side of the pulley axis. So to make stable, system will rotate in anti-clockwise to make it stable, so it won't flip and fall down. Let's come to the middle support. We are using precasted concrete beams as support. In here, cable is we are giving cable to rest, and when it's going over the support, it may be double. So we are using this skateboard shaped metal plate to prevent flipping. It will give a force to downside when pulley is moving through it, and when it's throwing, that small wheels gives frictionless movement, so it will not flip. This is the third class, material unloading point. We can get the material from bucket out using down part of the bucket.
Now let's move on the design summary of our proposed hoisting system. The system consists of the fixed rope and hauling rope designed for safe and stable material transport along 66 meter slope. For the rope selection, we used galvanized steel wired rope with the diameter 16 mm. This rope previous a breaking load between 110 and 120 kilonewtons, which is sufficient to handle the expected load with a proper safety margin. Next, the winch system is single drum electric power winch operating on 230 volt AC supply. It has a 2.2 kilowatt motor capable of achieving a hauling speed of 15 meter per minute. The winch includes a forward and reverse switch for sample manual operation. For pulley components, steel pulleys with diameter 200 mm are used. Each pulley has 30 mm groove and a 25 mm shaft diameter support by ball bearing to reduce friction and ensure smooth motion. The main frame is a welded mild steel structure designed for rigidity and easy fabrication. A 10 mm plate thickness was selected for sufficient strength while keeping the system lightweight and cost effective. For the mid support, a reinforced concrete post is used with galvanized steel saddle at top. The provides both durability and sufficient stiffness to maintain the rope alignment across slope. Overall selection ensure the system remain low cost, reliable and suitable for the slope stabilization work at Damodara. The cost analysis was done using current local market prices of material and equipment available in Sri Lanka. Here is the brief summary of the estimated cost. The total estimated cost of the system approximately 493,144.44 Sri Lankan rupees, which is significantly lower than most commercially available hoisting system. This makes it practical and cost effective solution for small scale slope stabilization projects. Next, we will move on to the conclusion and recommendation section.
Compared to normal hoisting systems like tower, cranes or rail-based trolleys, our fixed skyline system with mid support is much more practical and valuable for the site. Those systems need large foundations, more space and higher cost, not suitable for steep slopes near railway lines. Our system need less engineering, less cost and easier to install even in limited space. It can also be removed and reused for future slope projects after this 1 year soil nailing project. Overall, it gives more value. It's simpler, safer, cheaper and reusable compared to other systems. Compare our system best for other system. Other than advantages I mentioned, there are several limitations as well. Load capacity limited to 200 kg. Manual control operation must climb near the witch to press the control button. No emergency stop system if the rope fails. There are some recommendations that can be added in the future for this system. First, in the future, remote control operation can be added so no need to go near the winch. Second, add an emergency catch or brake system to stop the bucket if the rope breaks. Third, introduce automatic tension sensors for safer operation. In conclusion, our hoisting system is cost effective, safe and easy to install, which make it more valuable than normal systems. With small improvements like remote control and emergency braking, this design can be a standard model for future slope stabilizations project in Sri Lanka. Thank you for your attention.